Hello and welcome to Math 135. This is week 12, lecture part 2. In this video, I will explain the hypothesis testing process and the logic of hypothesis testing, and then we will test hypotheses about a population proportion and then test hypotheses about a population proportion using the binomial probability distribution. Let's look at this example and see if I can explain the meaning of hypothesis testing or the logic of hypothesis testing. A researcher obtains a random sample of 1,000 people and finds that 534 are in favor of the banning cell phones use while driving. So p hat, which is the sample proportion, is equal to 534 divided by 1,000. Does this suggest that more than 50% of people favor the policy, or is it possible that the true proportion of registered voters who favor the policy is some proportion less than 50%, and we just happen to survey a majority in favor of the policy? In other words, would it be unusual to obtain a sample proportion of 0.534 or higher from a population whose proportion is 50%? What is convincing or statistically significant evidence? When observed results are unlikely under the assumption that the null hypothesis is true, we say that the result is statistically significant. When results are found to be statistically significant, we're going to reject the null hypothesis. To determine if a sample proportion of 0.534 is statistically significant or not, we're going to build a probability model. Since n times p times 1 minus b is 250, which is greater than or equal to 10, the sample size is 1,000 is sufficiently small than the population size, we can use the normal model to describe the variability in p hat. Remember, from the distribution of the sample proportion, we know that the mean of the population of the sample proportion is equal to the proportion of the population, which is in our case 50%. The standard deviation of the sample proportion is equal to the square root of p times 1 minus p divided by the sample size, which is in our case going to give us 0.016. So this is the sampling distribution of the sample proportion, and we have the mean in the middle. So if we added one standard deviation to the mean, we will get 0.516. If we subtracted one standard deviation from the mean, we will get 0.484. So how far is too far away from the mean? How far is too far away from the mean? We would say that a sample evidence to be statistically significant or sufficient if the sample proportion is too many standard deviations from the mean. Let's say 2 standard deviations above the mean or below the mean. So if we go to the previous example and we compute how far away from the mean is the proportion, the sample proportion that we computed, which is 0.534, we're going to use the formula to compute how many standard deviations away from the mean. Remember, we're going to use the z-scores to measure the distance between the sample proportion and the population proportion in this case. So the z-score is equal to p hat minus mu sub p hat divided by the standard deviation of the sample proportion. And we have everything here. P hat was computed, and we have the mean of the distribution of the sample mean to be 0.5, which is the population proportion, divided by the formula for the standard deviation for the distribution of sample proportion. We will get z is equal to 2.15. So the proportion, the sample proportion that we computed is basically 2.15 standard deviations above the mean, which is 0.5. Therefore, using this criterion, we would reject the null hypothesis because we found out that the new proportion is too many standard deviations away from the mean. In other words, it's not in the middle, 95%, and that is statistically significantly different from the population mean, and as a result, we're going to reject the null hypothesis. But why does it make sense to reject the null hypothesis if the sample proportion is more than 2 standard deviations away from the hypothesized proportion, which is the null hypothesis? See that the area under the standard normal curve to the right of z is equal to 2. The area under the standard normal curve to the right of when z is equal to 2 is 0.0228. If the null hypothesis were true, population is 0.5, then 1 minus that number will be 97.72% of all the sample proportion will be less than 5%, plus 2 times the standard deviation, which is 0.532, and only 2.28 of the sample proportion will be more than 0.532. If the null hypothesis were true, which is the population proportion is 50%, then 97.72% of all sample proportions will be less than 50%, and only 2.28% of the sample proportion will be more than 0.532, or 53.2. In this chapter, we will learn how to use the classical approach to test the hypothesis, and we will use the p-value approach to test our hypothesis. Using the classical approach, if the sample proportion is too many standard deviations from the proportion stated in the null hypothesis, we reject the null hypothesis. And as a result, we will need to compute two things. We will need to compute Z0, and we will need to compute the critical value to determine if the test statistic, which is Z0, is too far away, is going to be in the rejection region or the critical region. If that is the case, we're going to reject the null hypothesis. If that is not the case, we're not going to reject the null hypothesis. The p-value is the probability of observing sample statistics as extreme or more extreme than when observed under the assumption that the statement in the null hypothesis is true. So the idea behind the p-value is if the probability of observing a sample statistic as extreme or more extreme than the observed under the assumption that the statement in the null hypothesis is true. So in other words, we're going to compute probability and compare them to alpha. If the probability of getting a sample statistic as extreme or more extreme than the one obtained is small under the assumption that the statement in the null hypothesis is true, we're going to reject the null hypothesis. In other words, if we computed p-value and we found out that p-value is less than alpha, we're going to reject the null hypothesis. A second criterion we may use for testing hypotheses to determine how likely it is to obtain a sample proportion of 0.534 or higher from a population whose proportion is 50%. If a sample proportion of 0.534 or higher is unlikely or unusual, we have evidence against the statement in the null hypothesis. Otherwise, we don't have sufficient evidence against the statement in the null hypothesis. In other words, if we computed the p-value and we figured out that p-value is greater than alpha, then we don't have sufficient evidence to reject the null hypothesis. In other words, we're going to fail to reject the null hypothesis. We can compute the probability of obtaining a sample proportion of 0.534 or higher from a population whose proportion is 50% using the normal model. In this case, notice that we are performing a right tilt test, and as a result, we want to compute the area to the right of the proportion 0.534. Recall that z is equal to p hat minus p divided by square root of p times 1 minus p divided by n, and we got 2.15. So we compute the p-value, which is the probability of the area to the right of the statistic that we computed, p hat, and we will get 0.0158. The value 0.0158 is called the p-value, which means about 2 samples in 100 will give a sample proportion or as high or higher than the one we obtained in the population proportion really is 50% or 0.5. Because these results are unusual, we take this as evidence against the statement in the null hypothesis and we reject the null hypothesis. In simple steps, what should we do to test hypotheses regarding the population proportion? To do that, we're going to use the following steps provided. 1, the sample is obtained by simple random sampling. Next, we will check for normality. The sample values are independent of each other. We have 3 cases. We have two-tailed test, left-tailed test, and right-tailed test. The first step for testing the hypotheses is to determine the null and alternative hypotheses. We will have 3 cases: two-tailed test, left-tailed test, and right-tailed test. This depends on the language of the question or the research. Number 2, we're going to select a significance level. Usually, we're going to select 5% for significance level, unless it is mentioned otherwise, alpha is equal to 5%. And then we're going to compute a test statistic. After you compute the test statistic using the following formula, you're going to compare that to the critical value. If you have a two-tailed test and you computed Z0 and you figured out that Z0 is going to be either bigger than the critical value, the positive critical value, Z naught is here, or Z naught is less than the critical value, which is going to be a negative number. In those cases, we're going to reject the null hypothesis. If we computed Z and we figured out Z is somewhere here, let's say this is Z naught right here, this means it is not in the critical region and we're going to fail to reject the null hypothesis. The other case is when we have a left tail test. If we have a left tail test and we computed the critical value, then we're going to see if Z naught is less than that critical value. If it's here, if it's less than the critical value, we're going to reject the null hypothesis. And if it's not there, let's say it is right here somewhere, then we're not going to reject the null hypothesis or fail to reject the null hypothesis. Lastly, if we have a right tail test and we computed the Z critical, then we're going to say if Z naught is bigger than that critical value, Z naught is bigger than that critical value, or in other words, it is in the critical region, we will reject the null hypothesis. If it's not in the critical region, let's say if it's right here, then we will not reject the null hypothesis or fail to reject the null hypothesis. In our case, if we have a two-tailed test, this is how you're going to compute the Z critical, or Z sub alpha divided by 2. So you're going to compute only one value, and then you're going to compare your numbers, because if you computed the negative value only, then the positive value will be the same, but it's going to be a positive instead of negative, using the symmetrical properties of the normal distribution. So let's say we want to compute this value right here. To compute that, we must have alpha. Alpha is usually 0.05 unless mentioned otherwise. But let's say we have alpha. So to compute that, we're going to use norm.s.inverse because we have the area and we want the number of alpha divided by 2, because alpha in this case is in two tails, and those two tails are equal in size. So we divide alpha by 2 to get each region. So this region is alpha divided by 2, and this region is alpha divided by 2 as well. So we're going to say norm.s.inverse of alpha divided by 2. So we will say that the Z sub alpha divided by 2 is going to be norm.s.inverse of alpha divided by 2, and we will get the negative value from this case. If we want a positive value, we're just going to remove the negative value and put it, or multiply the negative value by -1 to obtain the positive value, and we're going to use the symmetrical properties of normal distribution. So this is in case you have two-tailed test. If you have a left-tailed test, then Z sub alpha, which is negative Z sub alpha, will be equal to, or the critical value is going to be equal to norm.s.inverse of alpha, which is this region right here. This region is alpha, and you will get the negative value right away. And if you have a right tail test, then you're going to compute this region is alpha, and we know that to compute this value right here, we will need the area to the left of it, which is this one right here. This area is basically 1 minus alpha. So to compute Z sub alpha, when you have a right tail test, you're going to say norm.s.inverse of 1 minus alpha. And that will give you the Z critical. And then you're going to do your comparison, and you're going to come up with decision. The decisions are going to be like follows. If you computed Z critical and Z sub 0 or Z naught, you're going to reject the null hypothesis as long as Z naught is in the critical region that is less than the negative critical value and greater than the positive critical value. If it's in between those values, then you're not going to reject the null hypothesis. In the case when you have a left tail test, you're going to reject the null hypothesis as long as Z naught is less than the critical value. And if you have a right tail test, you're going to reject the null hypothesis if the test statistic Z naught is greater than the critical value Z sub alpha, computing the p-value. Now, the p-value depends entirely on probabilities, so you will not need to compute Z sub alpha, which is the critical value. In other words, we will rely on the critical region, alpha. We will rely on the area to the right of Z naught to the left of Z naught, or the sum of the areas to the right and left of Z naught if we have two-tailed test. If you have a two-tailed test, then you're going to come up with two critical values. You will have two critical values. You're going to compute the area to the left of the critical value on to the right of critical value. If you add them up, you're going to get the p-value. Imagine that we computed the z critical and we figure out that z critical is right here. So this is z critical, this is the negative one, and this is the positive one. In other words, alpha is the black region. Alpha is the black region. This is alpha and this is alpha. If that is the case, you notice that Z naught is inside of the critical region, and we say that p-value is less than alpha. The p-value, which is the addition of the two blue regions, is bigger than the addition of the two black regions, which represents alpha. So p-value is less than alpha. In this case, we're going to reject the null hypothesis because both of the test statistics are inside the critical region. How do you compute the p-value? So you're going to say that the p-value is basically the area to the right and the left of Z naught. In other words, you're going to compute only one blue region. You're going to find the area, one blue region, and then multiply it by 2 using the symmetrical properties of the normal distribution. So you're going to use the function, norm dot s dot distribution of Z naught. In this case, you're going to use the negative value, the negative Z naught, and comma true. And if you multiply that by 2, you're going to get the p-value because that will represent the area in both tails. In case you have a right tail test, how do you compute the p-value? You're going to say the p-value is equal to norm dot s dot inverse of Z naught. And this one is going to be a negative value as well. Pay attention, if it's a left tail test, the Z naught should be negative number. And that is the p-value. If you have a right tail test, then you're going to say the area here is basically 1 minus norm dot s dot distribution of Z naught comma true. Because this function will calculate the area to the left and we subtract that from 1 to get the area to the right, and that is exactly the p-value. I'm sorry, and this is the wrong function. We're going to use norm dot s dot distribution of Z naught comma true, and this is the negative Z naught. So that is the accurate function to compute the p-value if you have a left tail test. And if the p-value is less than alpha, we're going to reject the null hypothesis. Otherwise, we're going to fail to reject the null hypothesis. And then finally, we're going to state our conclusion. So if you look at this question, in 1997, 46% of Americans said they did not trust the media when it comes to reporting the news fully, accurately, and fairly. In a 2007 poll of 1,010 adults nationwide, 525 stated that they did not trust the media at a alpha equals to 5% level. Significance: is there evidence to support the claim that the percentage of Americans that do not trust the media to report fully and accurately has increased since 1997? To do that, we're going to follow the steps. This is a simple random sample, and we checked for normality, and then we know that the sample size is less than 5% of the population size, assuming and the assumption of the independence is met. Next, we will write our null hypothesis and alternative hypothesis. That is step number 1. Step number 2, we know that the significance level is 5%. Then we're going to compute p-hat because we will use it to compute z-naught. P-hat is 0.52. We will use the formula for z-naught to compute the test statistic. After we compute the test statistic, if we're going to use the classical approach, then we will use since this is a right tail test, we're going to use the critical value. We're going to compute the critical value. So if you use Excel to compute the critical value, you're going to get Z sub alpha is 1.645. And in this case, because we have a right tail test, we're going to say norm dot s dot inverse of the left area, which is going to be 0.95, since the right area is 5%. So if you do that, you're going to get 1.645. Since the test statistic Z0 is 3.83, that is greater than the critical value, 1.645, we reject the null hypothesis. So if you look at that, this is the 1.645, and 3.83 is right here. So Z0 is in the critical region since we have a right tail test. That is the critical region. As a result, we're going to reject the null hypothesis. If we're going to use the p-value approach, we're going to skip the finding the Z critical, and we're going to find the area to the right of Z0, which is the area to the right of 3.83. So when we have a right tail test like that, and we computed Z0 to be 3.83, we want to compute the area to the right, which is going to be p-value. So to compute that region, we're going to say 1 minus norm dot s dot distribution of 3.83 comma true. It is going to be significantly low that we're going to approximate that to a 0. We're going to round it to 0. So if you compare the p-value to alpha, we notice that the p-value is less than alpha. And as a result, we're going to reject the null hypothesis. Finally, we're going to say our conclusion. There is sufficient evidence at 0.05 level of significance to conclude that the percentage of Americans that do not trust the media to report fully and accurately has increased since 1997. I hope this video helped you understand the difference between the classical approach and the p-value approach. If you have any questions, reach out to me, email me, or you can come to my office hours and I will explain that further to you. Thank you so much, and I will see you in class.